Greetings, everybody. Let's take a look again at continue our discussion of subspaces of vector spaces. So let's recall some definitions that we've got given vectors v1, v2, all the way up to vn in our vector space V. Then if we take any scalar c1, c2 up to cn, then if we write an expression of the form c1 v1 plus c2 v2 all the way up to cn vn, then we call that a linear combination of our vectors v1 up to vn. A collection of vectors v1, v2 up to vn is said to be linearly independent if for any of our scalars c1 up to cn we take a linear combination that happens to give us 0, then that implies that c1, c2 all the way up to cn was 0, so that the only way that we can get the 0 vector is to have all 0 coefficients in there. So if we're given a set of vectors v1, v2 up to vn in the vector space V, then we define the span as the set of all possible linear combinations of vectors v1 up to vn. And so we might denote that by span of our set being the set of all possible linear combinations where ci's come from our scalar fields. So we got a theorem that kind of shows up immediately from that. If we take a set of vectors v1 up to vn, that's a subset of our vector space, then if we look at the span of that set S, then that's going to be a subspace. And so if we look at x and y being elements of our span, then that means that we've got linear combinations of the v1 to vn that give us x, linear combinations of d1 to dn that give us y. And since our scalar field f is going to be closed under addition, then ci plus di is going to be a scalar. And so if we add these together, regrouping, combining like terms with respect to the vi, then sure enough we get another linear combination that is in our span S. If we do the same thing for any scalar alpha, then because our scalar field f is closed under multiplication, we take alpha times x. Well, that's alpha times ci, our sum, c sub I, v sub I. Well, we distribute that alpha across and we get alpha times ci. Those guys are still scalars. We're taking a scalar linear combination, and so sure enough we end up back in the span of S. And so by the theorem that we proved in the previous video, that the span of S is going to be a subspace of V. Just as a little bit of a reminder and some little bit about future videos as well, that we can define a basis for a vector space to be a linearly independent set of vectors that span whose span is actually equal to the entire space. Something that we have seen before in our discussions of planes in three-dimensional space, maybe going all the way back to Calc 3, something like that, that we have seen the definition that a plane can be defined as the span of two linearly independent vectors. Now, in three-dimensional space, this is actually equivalent to defining a plane as the set of vectors that are orthogonal to a given vector n, and that given vector n was the normal. And so I'll kind of leave this for you guys to think about, that what is it about this definition that fails when we're talking about Rn with n greater than 3. So this is something that we can talk about a little bit in the future, coming up in future videos. And until then, I will see you guys later.